I'll type upper and lower case.
It's fast.
Okay, welcome back, everyone. So this afternoon we have another talk on Gibbs states that have been promised will have a great deal of synergy with Tiago's talk. So it's a talk by Alexander Zlokapa on classical algorithms for Gibbs states.
Yeah.
Feel free to go ahead.
Thanks, everyone, for making it back from lunch. I struggled. Hopefully not all of you did. I'll be talking about classical algorithms for quantum Gibbs states. I guess some of this was motivated by Tiago's somewhat more exciting tail end of the talk, where he suggested classical algorithms exist for a lot of these things. This work is based on primarily a paper that's out in the archive, but I would say that there's a lot of stuff that I'm going to sort of mention that, although the proofs look very different, has a lot of the same philosophy from a bunch of papers that I wrote with some collaborators, and I learned a lot from them. So yeah, I guess all these will at some point appear. So I should say that most of these results are rigorous, which sounds scary because it says that some of them are not rigorous. But I'm in the physics department, and in physics, we buy a lot more than in computer science. And so there are some things that are like where non-rigorous tools can go a bit further than rigorous tools, and I'll also tell you what beliefs that we have based on these tools, what these beliefs are. Yeah, I guess because I'm in the physics department, sometimes I'm like in the adjacent building to the chemistry department, and I'll find a chemistry person at lunch, intentionally or accidentally. And then during lunch, when I have lunch with a chemist, I wear a lab coat. They'll tell me about the problem, and they'll be like, I have some slow simulation I'm trying to run. You work in quantum computing. Surely a quantum computer can do everything, right? I read it does all the paths at once, like everything's good. And sometimes they'll give me some problem that I'm like, oh no, matrix multiplication. There's a lot of fine print, I don't know what to tell you about this. But sometimes they'll tell me that they're working on a problem that a quantum computer might be very good at. And I'd like to tell them something like, well, damn it, you should use a quantum computer. Feynman said so, and it will work. But in practice, all I'm stuck is saying a sort of awkwardly phrased sentence where like, so if we all know factoring is hard, you can sort of stuff this into your molecule, right? And then that molecule I could do something with maybe. That conversation usually ends poorly. They hand me their molecule and wait for me to come back to them. But I'm kind of at a loss of what to tell these people. And so a lot of what this talk is about is like trying to come up with a better answer than saying, well, factoring's hard, so maybe a quantum computer will work for your strongly correlated strange metal or whatever it might be. So as a result, I start to study like random Hamiltonians, since at least these are systems where you can take some sort of limit and ask kind of informative questions about, for a typical Hamiltonian that doesn't look like this contrived gadget was put inside it, is this going to be quantumly easy, quantumly hard, classically easy, classically hard? We can look at tasks that people in chemistry care about, like they want to know the ground state, they want to know its energy. Their system is maybe like in a thermal equilibrium in the environment. They ask questions about this. And so the sort of family of Hamiltonians they'll be looking at are just going to have Gaussian coefficients in front of them, IAD, and this operator P is going to be some k-local thing. It might be a Pauli Hamiltonian. It might be we'll go to like a fermionic Hamiltonian soon. But in the simplest case, it's just even classical. And this is just like k-local Z1, Zi1 through Zik Hamiltonian. And in the classical case, we know a lot of the answers, rigorously and non-rigorously to varying degrees. This is like a very historied sort of field of spin glasses that Tiago mentioned, where people studied these Hamiltonians back in the 70s and 80s. They solved it in some sort of superhuman ansatz fashion, and that was why Parisi got a Nobel Prize for it. And then Talleyrand proved those results rigorously, and that's what gave him an Abel Prize, even though it took 20 years of effort. It's like a hard problem to do rigorously, which is why we have a lot of non-rigorous results here. But then since the non-rigorous results out of this top line of French and Italian folk figured out all the non-rigorous tools, then the sort of rigorous results followed. And the rigorous results have gone even further. Like once we've gotten a rigorous handle on these, we can answer really fine-grained questions about like the local minima of this being easy or hard for classical algorithms and stuff like this. And so yeah, it's a very long sort of history of work that gives an interesting phase diagram, where at some very high temperature, which is small beta, these are like computationally easy to do a lot of these thermal questions. In particular, it's easy to sample from the Gibbs distribution. It's easy to estimate thermal expectations. And then as you cool down the system, at some point it becomes hard to sample from the Gibbs distribution. And then if you cool it even further, it becomes hard to estimate like the partition function or thermal expectations. And this is like a classical picture that took many decades of effort. And I think it's one of the more beautiful things out there. If you now go to like a local Pauli Hamiltonian, this is a paper that I studied with Bobak, who's here, and Eric Onschwitz. If you buy the sort of physics stuff that Parisi invented in the 80s, you find what's probably going to be a similar diagram. I'm putting it up as a sketch here. I'm going to say more about it later. But these sort of port over to quantum statements, where there's a transition from quantumly easy to quantumly hard at some temperature. A super interesting model that's been studied much more than this one is the SYK model. These are, yeah, like all the K local Pauli strings. So there's a sign problem, they're non-commuting, yeah. The SYK model has been studied in history quite a bit. It was proposed by Zlokapa and Yi back in the early 2000s, and then developed into a sort of the field of quantum gravity through some insights by both Zlokapa and Kitaev. And this has been also studied by a lot of folks in computer science as well, because it looks very quantum in some sort of quantifiable way that I'll get to in a moment, which makes people think that it might also be classically hard. The sort of last paper there referred to it as a non-trivial model for classical computers, despite seemingly to be quantumly easy. So I'll tell you more about these results, but yeah, essentially there's no phase diagram at any constant temperature that's non-trivial. Like it's just one phase for all temperatures. Yeah.
So in the earlier phase diagrams, what does hard mean? What are you going to say here?
Yeah, I'll make that. Be careful. I guess we can't, for these models, usually say that they're like as hard as a concrete problem. All we can say is that we rule out some class of algorithms, and those are stable algorithms that are like Lipschitz in the disorder or something like this. Yeah. Okay. So to tell you about the SYK model, I have to tell you what a fermion is, because it's defined in terms of fermions. So a fermion, we're only going to deal with Majorana fermions. They're just these Hermitian operators defined on individual sites. We'll have n sites. Their anti-commutation relation defines them. And you can imagine just encoding them as Paulis. So kind of noticeably, they're not local in the Pauli basis, because if I look at like a single fermion on some site n, it's going to have a string of n Paulis, or n over 2 Paulis describing it. So the Hamiltonian is going to be local in terms of these fermions for the SYK model. I know in computer science, people often don't like fermions. They're better than bosons, though, so hopefully we'll follow. The sort of, well, for qubits, we often look at entanglement and ask if a state is separable. The sort of analogous thing to look at for fermions is the Gaussian state. Or you can also, maybe it's more analogous to like a stabilizer state as well. So a Gaussian state is a compact representation that allows us to do computations with fermionic operators very easily. So a fermionic state is Gaussian if it's defined solely by this covariance matrix. The Pfaffian is just like a determinant, I guess up to a square. And so you can compute expectations against strings of Majorana fermions very easily classically. And so this becomes like a, Gaussian states are sort of classically easy states. And if you like a bit of chemistry in your life, Hartree-Fock is a special case of a Gaussian state. And these can also always be written as Gibbs states of quadratic Hamiltonians, where they're two local fermionic Hamiltonians. So this won't play too much of an important role in the talk. I just want to define it in case you've heard of Gaussian states but never saw the definition before. It also plays a central role in understanding in what sense the SYK model is very quantum. So before computer scientists looked at the SYK model, it was solved by physicists and sort of observed to be quantum, as models go. They solved it with a path integral and the replica trick, which are both non-rigorous methods. And you observe on doing this that you can't write it as some sort of probabilistic process. So it seems to be a non-stochastic model. It also has like entangled low energy states. It has magic at constant temperature. So it looks quantum. But this is made more precise in a line of papers that Hastings et al. Started in 2023, where you can observe that at any constant temperature, there is some sort of, if you try to approximate the Gibbs state by Gaussian states, it's very hard. So the second bullet point was Hastings et al. This was strengthened later by Robbie King and friends to look at the gate complexity for preparing low energy states, like typical states you would find at constant temperature. So you can show that any purification of the Gibbs state would require some large polynomial number of quantum gates. So that also looks like very not classical. There's one caveat here. This is not actually a statement about depth of the circuit. It's just a counting argument, so it'll only give you the number of gates, but it still looks like pretty good evidence that it's pretty quantum. The second bullet point I just wanted to say was strengthened by Hastings as well to look at like a superposition of some absurd number of Gaussian states, and like that's still very far from the Gibbs state. So yeah, it seems like a very quantum system. So now I maybe convinced you that you should think this is classically hard. You might expect that it's quantumly easy. And this is sort of a big open question that us people trying to prove things about Gibbs samplers have struggled with. It's very hard to prove that the CKG Lindbladian mixes quickly for SYK, but we believe it's the case. And why do we believe that we can actually have a quantum computer prepare the SYK Gibbs state efficiently? Well, we imagine CKG is something like putting the model into a refrigerator. And although that's maybe hard to think about, you can do sort of informal physics computations about coupling it with a bath. And these are the same picture in physics, where you just have some much larger system, which people usually take to be another SYK model, at some cold temperature. And you start your little model at infinite temperature and just have these systems interact. And you evaluate its dynamics and look at two-point functions and compute things. And you find that this process should take polynomial time in order to prepare the Gibbs state. How do you actually go about showing this with physics? It's quite a bit of work. You iterate some watermelons and use a lot of other sort of tools that have been developed that are all very powerful. And so I'm going to try to avoid telling you all about all this today, even though I'll secretly use some of it occasionally. And just tell you sort of a more informal intuition for why this is going to be quantumly easy. So you might have heard of a phase transition. The SYK model has no phase transition, and that's sort of the key reason why we think it'll mix quickly. What is a phase transition? Well, the partition function, trace e to the minus beta h, is analytic for all constant temperatures for the SYK model. This free energy density, of course, I'm being very glib here. We have to be a bit more careful. We actually look at the quenched free energy density. So we have some disordered Hamiltonian, these Gaussian coefficients, we take the expectation over them. And the quenched free energy is expectation of the log of the partition function. And in an n limit, this thing is analytic. Non-rigorously, it's analytic when you solve it with a replica trick and path integral. And this thing is supposed to approach the true partition function. Crucially, the log is out there, not inside. The expectation is outside the log and not inside the log. The annealed free energy generically is like very different from the quenched free energy, so you have to be careful. But we're very lucky for SYK that these two things actually agree. And I'll get to that in a moment. But let me first explain like why we're taking this limit, what's going on. So at first, there might be a puzzle in your minds, like z of beta is sum of e to the minus beta eigenvalue. this looks like an entire function. Like, how could this ever become non-analytic for real temperatures? And the key is in this n going to infinity limit. Yeah.
So can you explain what do you mean by beta being order 1?
Oh, for any beta independent of n.
Okay. Oh, you would take like a limit, like where you can afford scale.
Yeah. So, for instance, in Thiago's talk, there's a threshold of like beta going like 1 over degree.
Oh, I see.
And degree could scale with n, but here I'm going to look at beta independent of n. Yeah,
Oh, just I guess the expectation that's over the parameters of the Hamiltonian.
correct. Yeah. These like j coefficients I had earlier.
Would it be too much to ask, like, is there like a cartoon of what this graph looks like as a function of beta you can draw?
What z will look like?
Yeah,
Or log z?
Bunch free energy density.
Yeah, so
Or is it at beta equals 0 infinity?
at beta equals 0, z is just going to be like the trace of the identity, so it's just the dimension of the system. And so when you go to non-zero beta, like for SYK, the log will look like some term plus beta squared. So that's like the first correction in small beta. So it varies from system to system. There's like, yeah. But I will give you a cartoon of what the phase transition is in a moment. So yeah, okay, so it seems like this thing will always be analytic. How does it become non-analytic? Well, so partition function you usually think of, or at least I usually think of as at some real temperature. We have a thermal state, there's a temperature. A thermometer, only has real numbers usually. But you can also just plug in imaginary numbers or complex numbers and see what happens. And so you'll find that there are some places where your phases interfere and you get a 0. And so I'm going to just plot all of those z of beta equals 0. A phase transition is a statement that there's some density of zeros, where this density is extensive. It scales with n, so that you have some sort of non-analytic point over here where a phase transition occurs corresponding to where these zeros pinch the real axis. This is called the Li-Yang theory of zeros in physics. When applied to temperature, it's called the Fisher zeros. Fisher, the elder Fisher, is a family of very productive Fishers. And the phase transition happens where this pinches the real axis. But crucially, before this, you have some sort of region where there are very few zeros. And that's sort of a region that will become very important to us. So this is sort of, when physicists say phase transition, you might think water to ice, but usually this is what they mean. So let's say we want to estimate a partition function. If you've ever taken a StatMech course or a thermodynamics course, like all of the courses just compute a partition function and then somehow you're done with the problem. So oftentimes this is all you need. To estimate a thermal expectation, for instance, this is all you need. So let's try to estimate the partition function inside this disk. That turns out to be very easy. We can just Taylor expand. This is not revolutionary stuff, but it has a revolutionary name, Barvanok's algorithm. And it has, it's like a very deep contribution for a moment that we'll get to, which is, so let's try Taylor expanding. We can like bound the remainder in a Taylor expansion and find that we have to enumerate log n over epsilon terms to estimate z to multiplicative error epsilon. And then if h is local, this takes some sort of quasi-polynomial time, this n to the L of log n over epsilon. And so this gives you like a quasi-polynomial time algorithm that sort of works inside this disk. If you wanted to estimate a thermal expectation, as I advertised, you can do this also by just doing the same thing. Basically, you just perturb your Hamiltonian by the observable, and you take a small coefficient in front of it. So you can use the same trick to estimate thermal expectations. Now let's try to estimate the partition function close to the phase transition. Well, this seems hard because we ran into a 0. We all know that Taylor expansions will like diverge when they hit a 0. So what can we do? Well, we can just Taylor expand in the first disk and then estimate the point at the side of the first disk on the right, and then Taylor expand around that and keep repeating this like disk patching process. And this is what an analytic continuation is. And now we can estimate the partition function all the way up to a phase transition. And this will still have quasi-polynomial costs, still something like n to the O of log n over epsilon. And so this is sort of the insight that Barvanok had, that there's like a very versatile algorithm that works all the way throughout. And like if you can expand around a point like beta equals 0, suddenly you have a classical algorithm that works for an entire phase. So this will be quite important. OK, this is too much math, but if you ever wanted to learn complex analysis one day, or if you forgot about it, here it is. The only thing that matters is going to be the last line. So I said that if we can expand as long as we have a zero-free region. So how do we go about proving that we actually have no zeros? Well, you can do some complex analysis. And what you find is that for the quenched free energy expectation of log, the only thing that you need to care about is like expectation of z squared. And if you can compute that, then you'll be able to bound the number of zeros. This is a bound, of course. Maybe sometimes it isn't good enough. But for everything we'll look at, this is good enough. So it comes down to compute expectation z squared. So let's do this. I'm going to do it by iterating some watermelons first. And what you find is that the SYK model only has zeros on the imaginary axis. And you can do this non-rigorously with the replicate trick and path integral. And so this is a sort of more careful demonstration that there is no phase transition at constant temperature for the SYK model. In particular, we can run Barvanok's algorithm using like a rectangle that goes through this constant size gap around the origin. And we can estimate the thermal expectations for SYK all the way out here. And so all the way, although SYK looks like it's very quantum classically hard, we can just exploit the fact that there's no phase transition to actually produce a classical algorithm for it. It is quasi-polynomial time, but yeah.
So for thermal expectation, so do you only, that only works for local observable or for average observable?
So for this, it only works for local observables. But I guess the physics arguments that suggest SYK mixes in polynomial time also only look at local observables. Like we have no way to compute if we're close to the true Gibbs state because we're computing like 2-point functions between local operators. So sort of in the same level that Odin said we have is quantumly easy. It also shows that it's classically easy for the same sort of quantities.
But in physics, do people care about any like non-local measuring non-local observable for SYK model?
No, in practice you don't. You only measure local things in the universe. But I guess also I'm just saying that besides only caring about local operators, the tools we have in physics can only talk about local operators as well. Now, okay, this is non-rigorous. Enough of that. Let's get to some rigorous stuff. Well, we have to scale back our ambitions a little bit. So rigorously, I can show this part zero-free. And that's what I'm going to tell you about for the next few minutes. So this is, there are a few reasons why the SYK model is very tricky to look at. A lot of people have tried to compute quantities about it rigorously. There's a line of random matrix theory folks around the world who work on this. And it's quite a challenging problem. Let me tell you a bit about why. So I'll first tell you the result, though, because we need to know the result. So with high probability over the disorder, there's a zero-free disk for the partition function. So beta here is complex. Any radius within this is zero-free. And there's an algorithm that can estimate any thermal expectation of a local operator or the partition function up to some temperature that depends somewhat on the locality. Okay, so this is the sense in which this thing is classically easy. Yeah.
What does k comma max mean? K times?
Oh, sorry. There's. I thought I had a backslash comma in there for the formatting. There's no comma there. That should be just k times max. Sorry.
So
Yeah.
for the first page, you mentioned like for the zero, you can show the emergent part is infra-bounded. Is this independent of the set? Why is this true?
Sorry, which quantity is
I think that maybe just in the first 2 pages, you mentioned the zero of the partition function.
a beta?
The emergent part is bounded, like this.
Yeah. So the statement that SYK has no complex zeros at any beta is for any beta independent of n.
Okay.
These are always going to be betas independent of n. I guess the reason is that when you use the thermometer, it measures the temperature, and then if you go to a bigger room, the temperature doesn't change. Like temperature should be independent of n, and so in physics you just always normalize accordingly, and you only care about beta independent of n. So yeah, this is sort of beta at the right scale. This is beta independent of n. Okay. So maybe some of us heard some talks or read the paper about SYK from Robbie, Anthony, Bobak, and Eric. And you might think, well, we already know that quenched equals annealed from this paper. Doesn't this rule out a phase transition? What are we even doing? This is a known result. The issue is that that result shows that the quenched and annealed free energies are equal, which naively would rule out a phase transition because the annealed free energy can't have a phase transition. But the proof technique breaks for complex beta because it ends up assuming some sort of zero freeness to start with. And so you can't really use it for complex beta. I'm not going to go too much into this. It's more of an aside for those of you who have kept up to speed on the SYK literature in the last couple of years. So let's try to compute control SYK rigorously. The easiest sort of thing you can ever ask for is the annealed free energy. Just take the expectation of the partition function. This is classically a sort of no-brainer quantity. It comes directly from the Gaussian moment generating function. You just plug in the fact that the expectation of some exponentiated Gaussian gives you a square times the variance. And since the spins all square to 1, this is like an immediate fact. And so if you ever talk to a classical spin glass person and say, I'm computing the annealed free energy, they're like, what are you doing? This is sort of, very, very thoughtless stuff classically. But now let's try to run the same argument for SYK. Well, we're stuck with a bunch of operators that don't commute. Suddenly I can't bring the expectation into the trace the way I wanted to. I'm stuck with bounding it inside an exponential. So when you have matrices and you try to run a Gaussian moment generating function argument, you're stuck with a bound that is nowhere near tight. And so it's roughly bounded by the classical annealed free energy, but that is not a tight bound. And so somewhat embarrassingly, although this paper established that quenched and annealed are equal, it can't show it in the limit because we don't even know if the limit exists. So we made partial progress on this in some paper where we show it up to some constant beta that looks like the previous one. Yeah?
So I have a question on the normalization of this. It's I think typically you have n to the k divided 2 normalization. So on the Hamiltonian.
Are you looking at the standard deviation or the variance? I'm writing down the variance here.
Yeah, so for example here, your previous picture, do you view beta as a constant or something scale as, let's say, 1 over n to the k divided 2?
Beta is a constant in this normalization. Yeah.
Yeah, so I was wondering, so for the expected model itself, you didn't normalize it.
The coefficients are not standard normal. The coefficients were drawn with this variance over here.
Okay.
Yeah. And so the Gaussian MGF, this is classical, but you would get the variance, and then the sum over spin configurations gives you this 2 to the n, and there are n choose k operators. So this variance here is the same for SYK in the classical model.
Oh, yeah.
Okay. So in this paper, actually, I think the intuition for why these rigorous arguments work at high temperature is more clear. So I'm going to try to give you that intuition. So okay, let's try to compute the annealed free energy, give it our best shot, given what I said about it being hard. Let's see what we can do. So we start by Taylor expanding, since this is all we do in physics. And then we're like, OK, let me write my Hamiltonian terms and just expand the h to the m power in each term of my Taylor series. So this I bar is a tuple. It has the terms 1 through m in it in my Taylor expansion. And each I bar j is length k. And so what we'd like to do ideally is just truncate this Taylor expansion, somehow control the error and stop it at a few terms, ideally something much smaller than the system size. But that's pretty hard because the sum is actually dominated by terms when you have an extensive number of Hamiltonian terms inside the Taylor term. I have a fake proof where I plug in an answer that I know non-rigorously. You could also do this part more carefully and get some rigorous bounds. But the bottom line is that the typical term that sort of supports this quantity is going to have some linear scaling in n. And so we have to go all the way up to some large n. So OK, this computation sort of failed. Let's see what we can do better. So the insight is sort of intuition from looking at an Erdős-Renyi graph. So if we try to go to a term order beta squared n, and we write down a graph where each vertex is a fermion, so like psi1 through psi n, and let's just look at k equals 2 syk, so this is a trivial model, it's free fermions. We're going to draw an edge for each h sub I bar j, where I bar j has two fermions in it. So let's put a line between those two fermions. This graph, sort of, if we picked a random term in this sum, is going to look roughly like an Erdős-Renyi graph, where the probability of drawing an edge between 2 points goes like beta squared over n. And so in particular, if beta squared over n is larger than around 1, there's a giant component in this graph. If I look at the connected components, there's going to be some connected component that covers most of the graph. But if beta squared is small enough, then I will have like O of 1 sized components in this graph. And this decomposition is what allows us to make this Hamiltonian somewhat look local, even though it's this all-to-all densely connected model. And so, yeah. How do? Sorry.
You will have log local.
It'll be local, but log and the log is fine. Yeah. There's the log. So, yeah, if you haven't seen the proof of this fact, it's like a nice proof. You just consider traversing these connected components and looking at the number of neighbors that you're going to run into at any time step. And then you just, yeah, Markov inequality it. So in particular, the sort of cluster expansions that Tiago mentioned naively fail for all-to-all models that are in the mean field configuration, so like all the coefficients are equally sized. Cluster expansions can work when you have disorder, because the disorder ends up giving you a sort of Erdős-Renyi picture, where at high temperature, you can divide it up into log-size pieces. So I'm not going to go through the combinatorics of this. I'm just going to claim that this gives you the right answer in the end. Sorry about the comma after the k. So that's the classical algorithm for SYK. It's quasi-polynomial time, and it's quasi-polynomial time, but at least it's a rigorous result that we have, whereas in the quantum case, we can't even say rigorously if CKG will mix in polynomial or quasi-polynomial time. So I believe this can get improved to polynomial time, and there's some ideas how, but doing it rigorously is a bit more challenging than this method. That's all I'm going to say about SYK, but I'm going to move on to other things. Yeah.
What do you think about the dependence on beta? Do you conjecture that something like this?
Do you mean the bound on beta or the dependence on the runtime?
The beta being less than exponential.
So I guess the non-rigorous argument that I gave you earlier says that you should be able to defer any constant beta. And that's the answer I believe in. However, the largest disk you can non-rigorously check scales like this, but without this first k. And I think it's actually not hard to improve the rigorous result to get all the way to that number up to a factor of 5. But it doesn't really change the punchline, so I didn't do it. The beta dependence that's trickier to get rid of is the one in this quasi-polynomial factor. And that's where I think you need to use like much more physicsy approaches that are harder to prove. Yeah.
Can you say about how the technique compares to the different escape?
Yeah, so the escape proof breaks somewhat badly for non-commuting models. Because what it does is you essentially look at this product of Hamiltonian terms in your Taylor expansion, and then you want them to all product to 1, and you like make these rings. And then you can count those, and sort of you're done. And so like there was this recent paper, maybe you know about, that essentially used a cluster expansion that was developed many decades prior for an SK model. But when you're not commuting this like, you can't anymore just product these terms. The order matters. And so you end up creating polymers that are based on those connected components I just showed you. And so it's like really based on the Wick pairs. And you have to like take the expectation of disorder very soon in the proof. Yeah. Yeah.
So that disk radius, excuse me, corresponds to the point at which the Erdős-Renyi graph percolates?
Yeah, so that's roughly how you should think about it. there's some asterisks. I showed you a graph. We have a hypergraph. We have a multi-hypergraph, in fact. So don't take it verbatim, but that's you can actually like get the right scaling of this from that sort of argument. Yeah.
Yes, this like the non-rigorous physics intuition. So it seems like it holds up a lot. Does it always wind up being true, or are there like prominent cases where it winds up being false? Or?
This talk's being recorded, but
Sorry, I'll ask you later.
I guess there's like the spin glass field developed on two sides of the ocean, and I guess the replica method was made in Europe and had much success on things like the SK model. But I guess there's like a historical controversy over how far it extends beyond all-to-all models. Yeah.
I may have misunderstood this, but it seems like you're treating those two theorems as if they imply that there's no phase transition. And I don't understand. Can you explain?
Yeah, so the first theorem rules out any complex zeros from pinching the real axis up to this temperature. And so it formally implies any complex zeros of the partition function from approaching the real axis in the limit. So this rules out the presence of a phase transition up to this temperature rigorously.
And
The second
what
theorem is
about-
just an algorithmic corollary, basically,
Okay, so no phase transition up to this temperature.
rigorously.
What's
Yeah. Non-rigorously, no phase transition at any constant beta, but rigorously, this is as far as I can go. It's worth mentioning that to get the actual statement that there's no phase transition, you also have to know the limit exists, and so you have to combine this with my other paper showing the limit exists up to this temperature as well. And then you'll find that formally there's no non-analyticity in the free energy, so there's no phase transition.
Wait, can you repeat that last one again?
Yeah, so this statement is like, does not prove that the limit exists in n to infinity. So you have to combine this with the other paper that I have showing that log z's limit actually exists. And then with this, you'll conclude that in the limit, there's no non-analyticity up to this beta. Yeah.
Wait, what's K versus for any?
Yeah, this is for SYK with like a even K local,
Okay, and this is for any K, like. Okay.
independent of n.
Okay. What's the other thing? Do you have like an intuitive explanation for why complex zero should correspond to like a phase transition like a zero phase?
So you won't see the complex zeros physically usually, unless they're on the like real-time
Yeah.
axis, and then the spectral form factor looks at these. But yeah, I guess the theory of thermodynamics is built on this large n limit, and to take this limit properly, you have to control the complex zeros. Otherwise, you won't notice non-analyticities and things.
So is this necessarily using the analytical continuation or homotopy you mentioned first, or is the second one about translation?
So the rigorous result is just a disk, so I can just Taylor expand and truncate the Taylor expansion. The non-rigorous one, I work out you have to like map a disk to some other wedge shape and then look at that, and that'll give you like a better runtime than if you used a rectangle. You have to patch disks, do something different in the, since you don't have a disk due to the imaginary zeros on the imaginary beta axis. So the non-rigorous result uses a few more tricks, but this one is just a disk.
Are there models for which the free energy limit doesn't exist in a thermodynamic limit?
Yeah, if you somehow encoded parity.
So that is like
example.
periodic or something?
Yeah, it's just going to fluctuate. So as you take n to infinity, it's not approaching a single number. Okay. So we saw a sort of very special model here. It was in one phase for all of beta. That made it very convenient for us in some sense. This infinite temperature phase is called replica symmetric. I'm not going to tell you too much about what that means, but to give you intuition for it, I'm going to tell you about classical replica symmetry. So classically, replica symmetry means that if I drew two spin configurations, which are just plus or minus 1 bit strings, from the Gibbs measure, then their overlap will concentrate to a single number. And roughly speaking, you should think of this as your bit strings forming some sort of ball in Hamming space. if you look at the support of the Gibbs measure, you could truncate it into like one ball and you'd capture most of the Gibbs measure. But this picture is only accurate for models that are replica symmetric at all beta. Many models aren't. So here is the example where we take our Ising p-spin model that I drew earlier, or k-spin model. So this is like a Z Hamiltonian that is k-local with Gaussian coefficients again. And if you look at the support of the Gibbs measure, it's just a distribution now, you can decompose it into clusters that are all Hamming balls. And the distance between each of the balls in this picture is order n. And so you find that there are a few phases, and these have algorithmic meaning. So in particular, there's like when people say glassy or not glassy, they're referring to a transition that happens when you go from having like one ball that has virtually all of the Gibbs mass, so up to like exponentially small pieces that you're missing, when it breaks up into many small clusters that are of all equal size, roughly. So in this phase here, if k is larger than or equal to 3, we know that this phase over here has like exponentially many balls, each of which has like exponentially small fraction of the Gibbs measure. Whereas here we have some sub-exponential number of balls. So there's also a nice algorithmic implication, which is that sampling from the Gibbs measure becomes hard at that phase transition. Sampling here, I just mean that you're close in total variational distance, for example. This proving this algorithmic implication is a result by Alawi, Montanari, and Selke. However, if you care about mixing time, which is often what we're controlling with like spectral gap arguments in Lindbladians, what you find is that a mixing time argument asks about a worst case initial state. And so you might find yourself starting in like a small cluster that's exponentially small, but then you'll take a long time to go across this barrier to the big ball where all of the Gibbs mass is. And so you're actually slow mixing in the second phase. And so that's a slightly different notion of hardness. Whereas if you like cooled from infinite temperature, then it'd be easy since you'll probably start in the big cluster. The thing that I just told you about, where you can easily compute thermal expectations up to a phase transition, actually works all the way until here. The free energy is analytic all the way until that point. And so classically, proving that rigorously that we can go all the way here, I think is still open, but it's something that everybody believes can be done. And then it becomes suddenly hard after this phase transition when the statement of replica symmetry that I told you, that assumption no longer holds, and that's called replica symmetry breaking. So this is like when people talk about spin glasses, this is the picture you should have in your head. Yeah.
First, if you're just talking about sampling, you have all of these clustering transitions.
So I'm just talking about here for the Ising B-spin model. For other models, there are different physics that happens.
So you're not this kind of topology is always associated with the properties that you're listing.
No, this is for these disordered Altal models. I guess this also goes into John's question earlier, like how far can you extend the replica symmetry breaking ansatz? And it holds for these sorts of disordered Altal models, but for like more exotic things, it won't necessarily hold.
Right, but I guess what I'm saying is it can be replica symmetry breaking even one having an analytic partition function. That's what the WBC codes are.
Right, I guess if you go from replica symmetric to replica symmetry breaking,
it need not show up as a non-analyticity in the partition.
I agree, yeah. For these models, it does that. Yeah.
Are all of these like point space transitions?
No, only this one,
Only this
importantly.
one, okay.
Yeah. That's what allows us to do this algorithm to get observables at hotter temperatures.
And can you explain why sampling is hard even in a regime where the partition function is analytic?
Yeah, so I guess it's easy to see that like sampling implies counting. You can just sample and then estimate. But the other direction is trickier. And so what you'll find in this regime is that if you try to run your sampler, you're going to get stuck in one of these clusters that has exponentially small amount of support in the Gibbs measure. And then to figure out what another cluster is, you're going to have to wait some very long time, or just restart and fall into another cluster. But there are exponentially many of them, so it's going to take forever. And so rigorously, all we can prove is that like Langevin dynamics and stable algorithms will fail. And these proofs fall short of what we believe. We believe they'll take exponential time. We can only prove that they don't work in constant time. So there's a bit of a gap.
Observables are easy, then all the different wells. That way, even if you estimate from one of them, you're doing a pretty good.
So I guess when you're estimating with like Barbanok's algorithm, you're not going to be looking at individual wells. The wells individually have different magnetizations. Like they actually look quite different locally. But they have this nice feature where if you drew 2 samples from the Gibbs measure randomly, with probability 1, they'll be from 2 different wells. And so it still looks replicate symmetric. And this is sort of what makes sure there's no phase transition. OK. So now we all know what a spin glass is. I can tell you what happens. I already told you this. Phase transition happens at the indicated arrow. Let's go ahead. I can now tell you what happens if we looked at the same model but with Pauli strings instead of Ising spins. And this is if you believe the physics replica symmetry ansatz and replica symmetry breaking ansatz, this is what you come out with as how your Gibbs state decomposes into clusters. Each cluster is going to be labeled by row I, which goes from 1 through m. And these clusters are far, and they're separated from each other, and they have roughly equal weight in the Gibbs state. This decomposition is supposed to hold up to exponentially small error. So this is like defined under this weird Pauli bilinear form, where I'm just looking at one local Pauli's and looking at their expectations. So I'm like measuring a local magnetization and just taking the inner product over those. So this is if you just do the physics computation, you come out with, OK, this is how my Gibbs state is supposed to be decomposed. And now what this paper does is go into like formal algorithmic implications assuming this. What you find is that for a 3-local Pauli Hamiltonian, you have replica symmetry breaking at some constant temperature. So it looks different from the SYK model. And so now we can answer questions like, OK, we know that 3-local Pauli Hamiltonians are worst case hard. Are they average case hard? Well, they'll be hard in a similar sense to what we had earlier for classical spin glasses. If I had a larger computer, I could evaluate some integrals and tell you about these phases in the middle, but I don't have a larger computer. And so sort of a nice relationship between this work and the Bakshi, Liu, Moiter-Tang papers about quantum debrution condition is that this also gives you implications about quantum Wallerstein distance. In particular, the Pauli semi-norm that I wrote down is a lower bound on the Wasserstein distance for quantum states. And this is what allows you to get algorithmic implications out. So you can say that if your algorithm, as a function of beta, only moves the clusters a small amount in quantum W1, then any phase transition where they have to move suddenly will break the algorithm. And so this is how you get an abstraction to show that these are hard for a bunch of algorithms. What sort of algorithms? Well, an example is local Lagrangian dynamics at the same sort of level that we have Langevin dynamics as a result. So these are going to be local jump operators, and we're going to run it for constant time. And like the CKG setting, this is going to be Lipschitz in temperature. And that's what gives us this like smoothly deforming clusters property. This means that if I have any sort of break where a big cluster suddenly has to split at a phase transition to small clusters, I'm going to get a contradiction, and these algorithms will fail. So that is a much shorter account than what happened in the SYK model. But it sort of gives this picture where we go from temperatures where they're classically easy to compute local observables to temperatures where it's hard to prepare Gibbs states at some inconvenient locations. We were really hoping, that there's some phase where it's quantumly easy, classically hard. But no, like if you care about local quantities, then these classical algorithms go all the way into temperatures where it's quantumly hard to prepare the Gibbs state. So that's sort of like the picture to get from average case quantum complexity and classical complexity of these things. So you might say, OK, well, I'm not going to give up now. Where is the quantum advantage? Let's keep looking. Oh yeah, I should mention that there are open questions to show the other two things. If this is quantumly hard or classically quantumly easy, etc. Yeah.
So here is for, I might miss something here is for like SYK model or for like the random Pauli's.
Random Pauli would have this phase diagram. SYK model just has the first phase at all temperatures.
Here, like for quantumly hard, I guess you were talking about some like local algorithm, right? Local quantum algorithm. It generally quantum hard. I mean, who knows, but maybe at this is.
Yeah, I guess in classical spin glasses, for example, the best evidence we have are these bounds that rule out local stable algorithms. And the reason is that we sort of have nothing clever to do for them because they're just these random CSP-like problems. Like they're disordered systems where you can't clearly use Gaussian elimination or something that's unstable. The same is true for the quantum proofs. They only rule out like local dynamics. They won't rule out something that's very non-local and clever. But yeah, I guess if you could do that, the same sort of algorithm would probably work for like the classical Ising p-spin. And at that point, you're solving some like problems that are supposed to be very hard. And so it's a bit dangerous to think that this might work. Yeah.
In the regime where it's hopefully quantumly easy to sample, is there part of simulating things on some basis like that? Measure on that basis.
It's unclear. I think that's false. And yeah, I guess for bounded degree models and like some long range interactions, I have some results about this where it seems that classically a lot of these tricks work as well. Yeah.
So classically, the hardness evidence goes just like these local algorithms, like Lipschitz algorithms. You can also get low degree polynomials, low down circuits.
Yeah. Yeah.
Get the same sort of evidence here.
Yeah. So the conditions that like the reason that it applies to local algorithms is because, and stable algorithms is because they are, sorry, I'm saying it backwards. The reason it applies to low degree polynomials is because you can show that implies these Lipschitz conditions hold for them. And so they are stable algorithms under this Lipschitz definition, and you rule out all of those. So we're working with this broader Lipschitz class. So low degree polynomials will still be Lipschitz and beta in the same way. Yeah. Okay. So in the last couple minutes, I just want to tell you not to give up. So far we have this depressing picture. We go from classically easy to quantumly hard out of phase transition. What do we do? Well, as Vedika pointed out, these are sort of disordered all-to-all models that we're looking at. It's like a very particular class. You might hope that there's some other models where you have more room for quantum advantage. Okay, so let's try to think about partition functions in a slightly different light to get to models that have thermal states where we have more hope. To do this, I'm actually going to shift to a problem that looks very different at first, planted inference. But I'm going to pretend that you're doing planted inference for Gibbs distribution. So just humor me for a moment. Let's write down a probability distribution and assume that it's going to be a Gibbs distribution. This is all classical for now. If you wanted to try to sample from this, you might try to find a new distribution nu that's maybe parameterized in some way and minimize its KL divergence from mu. Those two words sound very similar. But when you try to do this, well, let's write it out. Definition of KL, plug in the fact that mu is a Gibbs distribution, and then do some massaging. What you find is that you have like a quantity that looks like the Gibbs free energy from physics. And so in particular, when you parameterize nu and you try to minimize over it, all you're really doing is minimizing the free energy, and the equilibrium of that is Gibbs state. And so you can write down a lot of these planted problems in the language of thermodynamics, and that historically gave people some insight. One place where I used it with Sasha Schmidhuber is for community detection. So I'll just define a stochastic block model, which takes no time. You have n vertices. You start with an Erdos-Renyi graph. So you put edges with some probability p, IAD between all vertices. You assign vertex labels randomly. For me, they fell on the left on the green, right on the red. And then for vertices within the same community, you add edges with some higher probability. Now you can ask questions like, if I only see the graph, what were the labels? Or were there even communities labeled? Questions like this. Those would be recovery and detection. In our case, for reasons I won't say too much about, we study the hypergraph version. Okay, it's the same deal, but you just use hyperedges. And in particular, now when you're adding hyperedges, the probability for these are labels belonging to some community over a set S of vertices. So you should think of this as like sigma 1 through sigma k inside this set S. You add a hyperedge with some probability that has like a perturbation by some arbitrary function of those labels. That's fine because we're on a hyperedge. It turns out that if you want, you can rewrite the distribution of your graphs, or rather, you rewrite the distribution over. You can write a partition function similar to what I said earlier. Let's say that. So you recover like a likelihood ratio, but in the language of a partition function where you're summing over all possible labels for the communities in your graph. And this over here is a local Hamiltonian. In fact, if I were doing tensor PCA, as Matt Hastings originally did in a similar setting, this would just be the Ising k-spin model that we were looking at earlier. And so you really have just like a k-local Hamiltonian. And now you have a partition function. You have like a signal-to-noise ratio, which I call delta. And you can ask questions about like phase transitions in this parameter and other, what are the structures of metastable states. And those lead to some interesting results. So you're able to show like a lower bound against low-degree polynomials that they cannot recover the community labels or detect if there are communities if delta is too small. Whereas we show upper bounds that you can if delta is large enough that match up to a log factor. And following the Hastings tensor PCA paper, this also ports over to a quantum algorithm that works better. But now instead of tensor PCA, it's for this community detection problem. OK, that's a lot and very quick because I'm short of time. But the takeaway is a nice picture where as you increase the signal-to-noise ratio in your random inference problem, you have a thermodynamic phase transition. Like literally the same Li-Yang theory gives you Fisher zeros. Except now it's in terms of delta instead of beta. And that defines a statistical threshold between being information theoretically possible to recover, or to detect, or to not detect if there were community labels planted, or if you're looking at just an Erdős-Rényi graph. And then if you have a very large signal-to-noise ratio, you have some classically efficient set of algorithms that will immediately recover the community labels. In between these, you have some sort of harder phase that smoothly interpolates between being impossible or exponential time and being easy. And that's the place where we report a quartic speedup in a super polynomial space advantage for typical instances in this sort of average case setting. Now, the reason why I think this is very interesting is that the sort of tool that the quantum algorithm uses is this Kikuchi method of approximating the free energy, where what's changing is as you refine your approximation to the free energy landscape, you pay more and more algorithmically, but you recover a closer and closer approximation to the true free energy landscape. And at some critical level, instead of having many metastable states that give you wrong solutions, your landscape only has one metastable state. And so this is sort of a way of probing the free energy landscape in a much more fine-grained way that tells us somehow these metastable states have structure that quantum algorithms appear to be better at accessing. So OK, this is just like another way of looking at free energy, Gibbs states, and problems. Here it's a classical problem, but yeah. So the way this algorithm works is it takes the entropy term in your free energy. So free energy is like energy and entropy added together. The entropy term has a log, which makes it a very global statement. This algorithm replaces that global quantity with L-wise marginals. And as I increase L, I approach like the true free energy. But at small L, I'm going to have some like belief propagation sort of thing. And if I look at the metastable states in the landscape for a chosen level L, at small L, I have many metastable states, and I am not able to recover the communities. But if I go to L large enough, eventually there's only one state. I have like one cluster in my picture, if you will, and the algorithm works. And so by like scanning across different L, we are able to probe the structure of the free energy landscape and like see how it decomposes into many metastable states or one. And somehow this structure seems to be good for quantum algorithms. Like this is, the quantum algorithm is explicitly using this decomposition of the free energy landscape. And so, yeah, I guess like these more fine-grained questions, I think have more hope for looking for interesting structure that quantum algorithms can use. Okay. So, yeah, I guess I'll wrap up. We looked at sort of places where SYK model, which looked very quantum, it looked very classically hard. These are large quantum circuits describing the states, but algorithmically they're classically easy. And unfortunately, this like family of disordered models seems to go from classically easy to quantumly hard, as we saw with the Paulis. But maybe like more careful examination of the free energy landscape can lead to, even for classical things like hypergraphs, some place to find quantum advantage. So I'll end with leave up a slide with a bunch of open questions that I think are very interesting, and happy to tell you more, but I'm a bit over, so I'll stop now.
Can you say a little bit about this like quantum Kikuchi thing? Is it like a quantum analog of SOS or?
So the Kikuchi thing is already like SOS in some level you might be familiar with. The quantum algorithm is just using the same construction, but with like a guided local Hamiltonian, well, sparse Hamiltonian problem. So you're able to somehow, the Kikuchi method creates a matrix that is based on this approximation of Ly's marginals. And the ground state of this matrix tells you where the communities are. One way of thinking about it is that, like one way of sort of sloppily deriving this matrix is by just taking the Hessian around a local minimum. And if you only have one metastable state, there's only one local minimum, and so this Hessian gives you like where the true community labels are. The quantum algorithm works better because you don't have to actually write down the whole matrix. You can just prepare oracles for the entries. So that gives you the space advantage. And then it also works well in time because you're able to actually prepare like a guiding state for where this local minimum should be, which gives you a bit more overlap than a trivial guess. Yeah.
This perspective for like super polynomial quantum advantage of any problem like this?
I'm optimistic. Like this was sort of this Kikuchi thing was more of an accident than like a careful construction in that tensor PCA is like a natural model that people have studied classically. I wouldn't be surprised if something a bit more contrived would get you this same sort of philosophy, but bigger speedups.
Yeah. I haven't kept up with the literature, but I know that some of these like vortex speedups were degraded to quadratic. What's the relationship with your stuff and that?
So there's, it's a bit messy because of this log factor. So improving to quadratic currently is like for still with a log factor, but if you can remove the log factor, then quantumly still have a quartic speedup. And we can actually remove the log factor. And so,
wait, sorry, where is the log?
Oh, sorry, in the signal to noise ratio, it has to be larger than some number. And there's a log factor in that number. And this thing is very annoying. But it seems much easier to remove for the quantum algorithms than for the dequantization attempts. Also, it's worth noting that the space advantage is still super polynomial here. Yeah.
What do you tell the chemists?
I'm working on it.
So like classically, I guess there's this is there some like quantum analog of things like quiet planting, for instance, where there's like an inherently quantum inference probability that looks like?
It's a bit tricky because classically when you like if you view tensor PCA as a Hamiltonian and you plant it, all you're planting is the coefficients in the J matrix. So if you try to do the same thing on the SYK model, like it's still the coefficients changed, and you could try to evaluate it. Like it doesn't look different from whatever operators I put there. So in that sense, there's no sort of natural generalization. But yeah, it'd be super interesting if there is a more natural thing than that.
Could you say again your intuition for why you think I guess why do you think this will have like the exact same story? Someone comes in and gives an efficient classical algorithm up until the quantum hardness.
Yeah, so I guess there are two things to mention about this. So one is that this family of models is quite different from like the all disordered ones, in that most models don't have this phase diagram. Like it's a very special phase diagram. And the source of this phase diagram being special is that somehow it has this structure of metastable states that if you look at larger and larger subsystems, then you get closer and closer to the true free energy, and like a metastable states change. So that's, I guess, one reason to think this is not, like the generic things that happen to other models might not happen to these since they're a bit different. A second thing is that I think although polynomial factors like a quadratic or quartic are hard to have intuition for and say, well, this one's clearly here to stay. The super polynomial space advantage is pretty compelling in that classically, like, until you go to a high enough level of the Kikuchi hierarchy, your landscape looks pretty random. That's what the low degree lower bounds tell us. And so all you're doing there is like, the best you can do is sort of walk around this landscape. And so if you look at lower bounds for like birthday problems in space, it seems very hard to come up with classical algorithms that don't have to store a lot of these random walks to come up with collisions. Whereas in the quantum case, we have this benefit where we can like prepare oracles that tell us matrix elements, and this does seem pretty powerful.